Hello, I am Cyril Six, a PhD student. I'm supervised by Sylvain, Boulmé and Monniaux. We are from the VLIW laboratory, which is specialized in code verification. And I also work at the Calais company, which produces and designs processors in France. In this talk, I will present how to introduce instruction scheduling optimization in a certified compiler such as CompCert. And I will present how that affects interlocked VLIW processors such as the one we are working on. To introduce instruction scheduling, here is a very simple piece of code. That piece of code does an addition, a load from memory, and then a subtraction using the value we just loaded. Each instruction on the CPU takes a certain amount of cycles, which we call latency. Here we are going to assume that the addition and the subtraction have a latency of 1, while the load has a latency of 2. We are going to execute that code through a simple processor model pipeline, where you have one stage decode which will decode the instruction and read the registers, and two stages, exec 1 and 2. Exec 1 will be where the add and sub instructions finish, and exec 2 will be where the load finishes. Now if we try to execute that code, we see that the processor inserts a stall here, because R3 is not available yet. The load needs 2 cycles to get the value of R3, and only 1 cycle happened between the load and the sub. However, if we swap the order of 2 and 1, we don't have this issue anymore, which makes us win 1 cycle. We want instruction scheduling to benefit our target, the Calais processor, though our work can also be adapted to other in-order processors. The Calais processor is in order, so the order of the assembly code is the order of execution. It has a pipeline of 9 stages, and it also has very large instructions, so the processor can execute several instructions at the same time, and this parallelism is specified in the assembly code. So here is an example of Calais assembly code. In that kind of code, double semicolons indicate bundle delimiters, and these bundles group together instructions that will be executed at the same time. For instance, here we have a bundle with 1 jump, 1 addition, and 1 multiplication. We can insert as many instructions as we want inside the bundle, just as long as we satisfy the resource constraints of the processor. Another thing to note is that if within the bundle there is a read and a write to the same register, then the read will take the values of the register before the execution of the bundle. So actually, this bundle does a swap of R0 and R1 in 1 cycle. These bundles are typically generated through a scheduling path of the compiler. So given such a piece of code, we would like our compiler to first split the code into basic blocks. Basic blocks are blocks with a single entry point and a single exit point. And then we would like to schedule each of these basic blocks in order to reorder the instructions to minimize the stalls, and also in order to generate bundles. Typically, in this example, the load has been moved further up ahead in order to minimize the stall, but also the sub R0 has been moved in the same bundle as the load instruction, because since R0 is not used here, this does not affect the correctness of the program. And so we would like to integrate the scheduling inside the CompCert certified compiler. CompCert is a formally verified C2 assembly compiler. Like each compiler, it has a certain number of intermediate representations, but the major difference is that each transformation path is actually proven correct. So if you have an initial piece of code that satisfies some properties, and if that code does not have any undefined behavior, then CompCert guarantees you that the output assembly code will have the same properties. So there's no introduced bug within the optimizations of CompCert. This notion of compiler correctness is usually ensured by disabling all optimizations from compilers, like using GCC O0. CompCert, on the other hand, allows critical system developers to use optimizations and still have the formal guarantee of correctness. So in our case, we would like to introduce scheduling at the ISM level in order to have precise information about instruction latencies. And the scheduling will be post-pass because it's after register allocation. The semantics of ASM in CompCert are quite simple. A state in ASM is the combination of a register state and a memory state. The register state is just a mapping from registers to values, and the memory state is a mapping from addresses to values. Then, the execution semantics are given as follows. First, the memory is read at PC value to give an instruction I, and if that fetch succeeds, and if we get an actual instruction from that, then we execute it with the execinst function. And then, if this execinst succeeds and returns next of another state, this gives us the next state to execute. This execinst might actually fail if you have, for instance, a division by 0, in which case it will return stuck, and then we won't have any transition. This semantics presents two major difficulties when it comes to introducing an optimization path. The first difficulty is that PC must always point to valid location in memory. So if you have an optimization, then there must be some kind of proof that this optimization does not change that property. Another difficulty is that ASM contains a lot of instructions. In the case of CalRay, we have more than 100 of them. So it's best to make sure that our proofs scale with that amount of instructions. So we have three contributions to tackle the difficulties of implementing a scheduling path at the ISM level. The first contribution is a method to recover the BasicBlock structure at ISM level, despite the issue of PC that I mentioned earlier. The second one is the scheduling path that scales with the number of instructions. And the third contribution is the modeling of the VLIW parallel bundles execution in CompCert. So our architecture is as follows. First, we recover the basic blocks at the Mac level. We did it at Mac because the Mac representation is much easier to work with than ISM. This gives us a representation Mac block where we execute basic block per basic block instead of instruction per instruction. Then we generate the assembly code basic block per basic block. Then we generate bundles with the postpath scheduling. This gives us an ISM VLIW program where each bundle has a parallel execution. Finally, abstract basic block is an abstraction that helps to deal with the huge number of instructions. To define a basic block, we split the instructions in two families. The basic instructions are those who do not alter the control flow. For example, additions, subtractions, loads, and stores are basic instructions. And then we have the instructions which might alter the control flow, like branches, calls, returns, or built-ins. Then we define a basic block as a list of labels, a list of basic instructions, and optionally at the end, a control flow. We use this notion of basic block to represent the notion of bundles as well, since a bundle can be seen as a small basic block. This B block can be executed sequentially, but we would also like to have parallel execution for bundles. To model parallel execution, our idea is to have a snapshot of the initial state from which the reads will fetch their values. Here, LSR-MR is the snapshot state, and LSW-MW is the running state where all the writes will occur in the same sequential order. So we start with the initial state, we snapshot it, then we run each instruction, and then the final state is given as the last running state. So if we run the semantics on this example, first R0 takes the value of R1, then we execute the second instruction. R1 takes the snapshot value of R0, which is R0. So at the end, executing this bundle in parallel does a swap of R0 and R1 and then does a jump to L104. This first fashion models accurately the relation between the reads and the writes. However, it is inaccurate in the case where there are multiple writes to the same register. Indeed, the architecture does not tell what happens in the case of multiple writes to the same register. It could be in any order. To fix that issue in our semantics, we introduce a non-deterministic permutation of instructions, so executing a given bundle could lead to several results. However, in our semantics, we only accept those that have a unique outcome. So, in order to generate ISM VLIW code, the optimization path must prove that each bundle has only one unique outcome. Now, I will detail how we prove the instruction scheduling which generates bundles. In order to do so, we use the concept of a posteriori verification. The basic idea is that writing a scheduler in Coq and then proving it is very hard. So instead, we split it in two parts. The first part is the scheduler, written in OOPSLA, but it could be written in any language. This scheduler is not trusted. And then the second part has a certified verifier, which will actually verify the result from the scheduler in order to figure out whether this result is correct or not. So the ISMBlock program sends a basic block B. This basic block B is given to the scheduler. The scheduler returns a list of bundles. and then the verifier compares the list of bundles to the initial basic block and returns either OK or error. If it's OK, the compilation goes on. If it's error, it stops. In addition to that, we use verified hash consing to make the verifier scale. The verification itself is done within abstract BasicBlock. The core idea of this new language is that in order to figure out the correctness of the scheduling, we only need to know which instruction uses which resource. In order to do that, we encode an instruction as a list of sequential assignments where a given resource is assigned to a given expression. And an expression is either a read of a resource, or an operation between a list of expressions, or an old operator which returns the value of the expressions before the execution. So for example, the instruction add word R0, R1, R2 is encoded as a single assignment where R0 gets the result of the add operation applied to R1 and R2. Another example is load Q, which loads a value in 2 consecutive registers. We translate it into 2 consecutive loads, but for the second load we use the old operator since A and D0 could be the same register. With this language, it's much easier to reason about scheduling because all the reads and the writes are described within the syntax instead of being in the semantics, which is what allows us in the end to make our proof scale with the number of ASM instructions. We then use this language to implement 2 checkers. The first one checks that for a given bundle, the sequential and the parallel semantics are the same, which is equivalent to verifying that there is no use after write within the bundle. And then the second checker verifies the reordering correctness of a basic block through symbolic evaluation. The core idea of symbolic execution is to exhibit the function which links the final value of the register based on their initial values. So for example, if I want to compare these 2 basic blocks, their sequential execution should be both equivalent to this assignment. So our verifier actually computes this symbolic memory for each basic block and returns error if these symbolic memories are different. So we actually have 3 semantics here. We have the semantics of ASM block, the semantic of abstract basic block, and we also have the semantic given by the symbolic memories that are computed by symbolic execution. So in order to prove the correctness, we prove the bisimulation between each of these 3 semantics. We evaluated the scheduling impact in CompCert on a given set of benchmarks. Here we actually compare 3 versions. The first one is the original CompCert without any scheduling. The second is a restricted version of our scheduler where we pack the instructions together into bundles without changing their order. And the third version, which is the reference here, is our actual list scheduler. On this graph, you can see that the OOPSLA and pack versions are always worse than the scheduler. In average, we gain 40% more performance by doing scheduling compared to no scheduling, and we gain 20% more performance compared to just packing the instructions together. This result is only for the Calray architecture, but we believe there could also be a notable performance increase for other in-order processors. We also compared CompCert with our scheduler versus GCC. What we can see is that compared to the GCC for this architecture, we are much faster in average. This can be explained by the fact that GCC 00 is very bad on the Calray architecture since it only uses a couple of registers, and also it only produces 1 instruction per bundle, so it results in a very poor performance code. A better contender for us is GCC 01, and we are 20% faster in average. 01 has a couple of basic optimizations, but it does not produce bundles, so that's why we are still 20% faster in average. Finally, compared to 02 and 03, we are 18% slower and 35% slower on average. In order to bridge that gap, we are currently working on future optimizations, such as introducing static branch prediction in CompCert, using it to have pre-pass scheduling at the superblock scope. So here pre-pass would be before register allocation, which would give us more leeway to schedule instructions. And superblocks are like basic blocks but with multiple exit points, so you can move an instruction on top of a conditional branch. And then, in conjunction with this pre-pass scheduling, we are also working on implementing very simple loop transformations such as loop rotate and loop unrolling, which would allow us to have a more efficient scheduling. So thank you for your attention. and we will be very happy to answer any question in the Q&A session.